Wright Field, Ohio, January 1940. The air inside the Army Air Corps Engineering Office is thick with cigarette smoke and skepticism. A specification document sits on the desk. Requirements that read like science fiction. A bomber capable of carrying 2,000 pounds of bombs for 5,333 miles at 400 miles per hour, at altitudes exceeding 30,000 feet, with defensive armament controlled remotely by gunners sitting nowhere near the guns themselves. The numbers represent impossibility stacked on impossibility. No aircraft in 1940 can fly that far, that fast, that high, while carrying meaningful payload. The best bomber in American inventory, the B-17, manages 2,000 miles with half the speed at two-thirds the altitude. The specification demands performance improvements across every dimension simultaneously. Boeing's response arrives in May. Project 345. A design so radical that even Boeing's own engineers question whether the laws of physics will permit it to fly. The wing loading alone exceeds anything attempted in production aircraft. The pressurized cabin requires sealing technology that does not exist. The remote gun turrets demand computing systems still theoretical, but the strategic calculus driving the specification is brutal and simple. Japan sits 6,000 miles from the nearest American air base. Defeating Japan means bombing Japan. Bombing Japan means building an aircraft capable of reaching it. There is no alternative. There is no fallback position. Either American industry produces the impossible or the Pacific War becomes unwinnable. The Army Air Corps awards Boeing the contract in September 1940, 15 months before Pearl Harbor, authorizing development of the XB-29. The decision commits the United States to the largest, most expensive aviation program in history. Bigger than the Manhattan Project in budget, more complex than any weapon system ever attempted. Critics within the military establishment call it fantasy engineering. Congress questions the expenditure. Aviation experts predict catastrophic failure. The B-29 program begins not with confidence but with institutional doubt, skepticism embedded in every review board, every budget hearing, every technical assessment. This is how America committed to building an aircraft that violated every principle of conservative engineering. The war demanded miracles. Boeing promised to deliver one. The altitude requirement was not arbitrary. It was survival. At 30,000 feet, Japanese fighters lose performance. Their engines gasp in thin air. Their pilots struggle with hypoxia. American bombers flying that high become nearly untouchable. But humans cannot function at 30,000 feet without pressurization. The crew compartment must maintain sea-level pressure while the aircraft operates in an environment where water boils at body temperature. Boeing engineer Wellwood Beale understood the challenge was not just sealing the fuselage, it was maintaining structural integrity, while the cabin held 8.5 pounds per square inch differential pressure. Every rivet became a potential failure point. Every access panel required sealing systems that could withstand thermal cycling from sub-zero exterior temperatures to heated interior spaces. The solution required inventing an entirely new construction technique. The fuselage became a series of pressure vessels. The forward compartment housed the pilots, bombardier, navigator, and flight engineer in a sealed cylinder 16 feet long. The rear compartment held the gunners in another sealed section. Between them, the bomb bay remained unpressurized, the two crew spaces connected by a pressurized tunnel 34 inches in diameter running above the bomb racks. Crews would crawl through this tunnel in flight, moving between stations while outside the aircraft, the temperature dropped to 60 below zero. The engineering was unprecedented. Boeing had to develop new welding techniques, new gasket materials, and new testing protocols to verify the pressure seals would hold. The first pressure tests failed. Fuselage sections ruptured, seams leaked. The entire pressurization system required 3 complete redesigns before achieving reliability. Each failure consumed months. Each redesign pushed the program further behind schedule and deeper over budget. But the physics demanded it. Without pressurization, crews could not survive long enough to complete missions over Japan. Without high-altitude capability, losses to Japanese fighters would make strategic bombing economically unsustainable. The B-29 had to work at 30,000 feet, or it could not work at all. Boeing was building an aircraft where failure of a single gasket could kill everyone aboard. Wright Field, March 1941. The Wright R-3350 duplex. Cyclone sits on a test stand, 18 cylinders arranged in 2 rows, producing 2,200 horsepower. On paper, it is the most powerful radial engine ever built. In reality, it is a death trap. The engine runs hot, dangerously hot. Cylinder head temperatures exceed design limits within minutes of full power operation. Cooling fins crack, valves seize. Connecting rods fail catastrophically, punching through cylinder walls and spraying oil across red-hot exhaust manifolds. The fires start immediately. Test engines ignite on the stand. Prototype aircraft burn on the runway. The R-3350 earns a nickname among Boeing workers: the finest cigarette lighter ever built. The failure rate is not anomaly, it is consistency. Nearly every engine suffers catastrophic failure before reaching 100 hours of operation. The problem is fundamental thermodynamics. The R-3350 produces enormous power in a compact package by running compression ratios and cylinder pressures higher than any previous radial engine. But the cooling system cannot dissipate the heat fast enough. The rear cylinders, shielded from airflow by the front row, cook themselves to destruction. Wright Aeronautical attacks the problem from every angle. They redesign the cooling fins, increasing surface area by 40%. They modify the cylinder heads, changing the combustion chamber geometry to reduce hot spots. They rework the exhaust system, the carburetor, the ignition timing. Each change requires months of testing. Each test reveals new failure modes. Boeing cannot wait. Production schedules demand engines now. The Army Air Forces authorizes installation of the R-3350 in its current state, accepting the risk because there is no alternative. The B-29 is designed around this specific engine. Switching to a different power plant would require redesigning the entire aircraft. The program is too far committed, too much money spent, too much strategic necessity driving the timeline. So the B-29 flies with engines that catch fire. Crews train an aircraft that might burn before reaching the runway. Maintenance crews develop procedures for fighting engine fires that assume multiple ignitions per flight. The engine crisis is not solved. It is managed, accepted, endured as the price of maintaining the program schedule. Boeing engineer Russ O'Air studied the problem with cold mathematics. Defensive guns required gunners. Gunners required space, oxygen, and heating in unpressurized tail and waist positions. That space added weight. That weight reduced range. Range was the entire purpose of the aircraft. The solution was radical. Remove the gunners from the guns entirely. The central fire control system emerged from this constraint: 5 gun turrets, each containing 250 caliber machine guns, positioned at strategic points around the fuselage, but no gunners sitting at the guns. Instead, 5 sighting stations inside the pressurized crew compartments, each equipped with a computing gun sight connected electrically to the turrets. The gunner sat at a periscope sight, tracking the target visually. His movements translated through an analog computer that calculated lead, adjusted for airspeed, altitude, and temperature, then moved the remote turret to the correct firing position. The trigger was electrical. The gunner never touched the guns. He controlled them from hundreds of feet away through copper wire and servo motors. General Electric built the system, adapting hydraulic technology from naval gun directors. Each turret required 28 motors to traverse in azimuth and elevation while compensating for aircraft motion. The computing site solved differential equations in real time using mechanical gears and cams. One malfunction could disable an entire defensive quadrant. The system allowed one gunner to control multiple turrets. The central fire control officer could assign any sighting station to any turret, concentrating firepower where attacks developed. 4 gunners could theoretically direct all 10 defensive guns simultaneously against a single target. The tactical advantage was overwhelming if the system worked. Testing revealed catastrophic problems. The servo motors overheated. The electrical connections failed under vibration. The computing sites could not track targets through evasive maneuvers. The entire system required complete redesign, delaying production by 8 months. But the concept was sound. Remote control saved 1,200 pounds compared to manned positions. It kept gunners in pressurized comfort rather than freezing, unpressurized compartments. It allowed tactical flexibility impossible with fixed positions. The B-29's defensive system represented the first true integration of computer-assisted fire control in combat aircraft. When it worked, It gave a single bomber the defensive capability of 3 conventional aircraft. Boeing Plant 2, Wichita, Kansas, September 1943. The production line stretches across 42 acres of factory floor. Partially completed B-29s sit in various stages of assembly. None of them can fly. Engineering changes arrive daily, sometimes hourly. A modification to the fuel system requires reworking 47 aircraft already on the line. A redesigned wing spar means scrapping components worth $2 million. The production system is collapsing under the weight of continuous revision. The program has entered what aviation engineers call configuration chaos. No 2 aircraft coming off the line are identical. Each incorporates different modifications, different equipment standards, different structural elements depending on when production began. Maintenance manuals become obsolete before printing. Parts inventories contain components for aircraft configurations that no longer exist. The Army Air Forces has ordered 1,664 B-29s before a single production aircraft has flown successfully. The contract value exceeds $3 billion. The largest military procurement in American history. Congress demands results. Newspapers question the expenditure. Military leaders privately discuss canceling the program entirely. Test flights reveal problems faster than engineers can solve them. The engines still catch fire. The pressurization system still leaks. The gun turrets jam in freezing temperatures. Landing gear struts collapse under the aircraft's weight. Wing spars crack after 50 hours of flight time. Every test mission uncovers new failure modes. Boeing assigns 10,000 engineers to modification work. They operate in 3 shifts, redesigning components while production continues. The factory becomes a laboratory. Aircraft roll off the line directly into modification centers where workers tear out systems just installed and replace them with updated versions. Some B-29s undergo modification 4 times before delivery. The death spiral tightens. Production delays push delivery dates. Further into 1944, training programs cannot begin because aircraft keep changing. Combat units receive bombers requiring immediate modification before operational use. The entire program threatens to consume infinite resources while producing 0 combat capability. This is how the most expensive weapons program in American history nearly collapsed under its own complexity before firing a shot in anger. Washington, D.C., November 1943. General Henry Arnold sits across from President Roosevelt, delivering news the president does not want to hear. The B-29 program is failing. Production is chaos. The aircraft cannot fly combat missions in its current state. Arnold expects cancellation. Instead, Roosevelt asks a single question. When can B-29s bomb Japan? Arnold promises June 1944. The statement is not optimism. It is desperation. The Pacific War is grinding forward through brutal island campaigns. American casualties mount with every landing. The strategic calculus is simple and horrible. Bombing Japan means fewer Marines die on beaches. The B-29 must work because the alternative is unacceptable. Roosevelt makes the program his personal priority. He assigns Major General Kenneth Wolfe to command the XX Bomber Command with a mandate that allows no excuses. Wolfe receives unlimited authority to commandeer resources, override procurement procedures, and bypass normal military chains of command. The message is explicit. Get B-29s into combat or face relief. Boeing receives a similar ultimatum. Deliver combat-ready aircraft by March 1944 or lose the contract. The company assigns 15,000 workers to an emergency modification program. 3 shifts working 24 hours daily, hand-fitting corrections to aircraft already built. The modifications include 900 separate engineering changes per aircraft. Workers strip systems out and rebuild them while the clock runs. The pressure breaks the normal development cycle. Testing that should take months happens in weeks. Procedures that should undergo validation deploy immediately to the field. The Army accepts aircraft with known defects, planning to fix them at forward bases. The risk is catastrophic, but the timeline is non-negotiable. Training begins while aircraft are still being modified. Crews learn systems that will be different when they reach combat. Maintenance personnel study manuals for configurations that no longer exist. The entire operational framework is built on sand. everything provisional, nothing finalized. The first B-29 combat unit, the 58th Bombardment Wing, deploys to India in April 1944. The aircraft are not ready. The crews are not ready. The supply chain is not ready. But the deadline has arrived. The B-29 will either prove itself in combat or fail publicly, expensively, and completely. Kharagpur, India, April 1944. The B-29s sit on dirt runways carved from jungle, 12,000 miles from Boeing's Seattle plant. The logistics are absurd. Every component, every spare part, every gallon of fuel must travel by ship around Africa, then by rail across India, then by air over the Himalayan hump into China, where the forward bases operate. One bombing mission requires 6 supply flights. The operational ratio is economically insane, but geography leaves no choice. The B-29's range allows strikes on Japan from Chinese airfields, but only if those airfields can be supplied. India provides the logistics base. China provides the launch point. The Himalayas sit between them, 15,000-foot mountains requiring transport aircraft to operate at maximum performance, carrying fuel instead of bombs. The first combat mission launches June 5, 1944. 98 B-29s target railway yards in Bangkok. 14 abort with mechanical failures, 5 crash on takeoff, engines catching fire with full fuel loads. The remaining aircraft reach the target, drop their bombs, and return. The mission is technically successful. It is also evidence that the B-29 remains dangerously unreliable. Engine failures dominate every mission report. The R-3350 still runs too hot. Crews develop procedures for shutting down burning engines, feathering props, and flying home on 3 power plants. Some missions lose more aircraft to mechanical failure than to enemy action. The maintenance crews work miracles keeping the fleet operational, cannibalizing parts from unflyable aircraft to keep others flying. The operational tempo is brutal. Each mission requires weeks of preparation, fuel stockpiling, and maintenance work. The supply line cannot sustain intensive operations. The B-29 units fly 1 major mission per month, then spend the rest of the time repairing aircraft and accumulating fuel. The strategic impact is minimal. Damage to Japanese industrial targets is negligible. General Curtis LeMay takes command in August 1944. He recognizes immediately that the India-China operation is unsustainable. The logistics consume more resources than the bombing delivers results. The B-29 is being wasted on a strategic dead end, its capabilities negated by impossible geography. LeMay begins planning for what comes next. The Marianas Islands are falling to American forces. New bases closer to Japan are becoming available. The B-29's real war is about to begin. Wright Field, Saipan, October 1944. The runway is 8,500 feet of crushed coral and compacted earth, built by Seabees in 60 days. The B-29s arrive from India, redeploying to the Mariana Islands, where distances to Japan measure 1,500 miles instead of 3,000. The logistics nightmare ends. The strategic bombing campaign begins. The 21st Bomber Command operates from 3 islands: Saipan, Tinian, and Guam. Combined, they provide bases for 1,000 B-29s, the largest concentration of heavy bombers in history. Supply ships arrive directly from the United States. Fuel no longer requires flying over mountains. Maintenance facilities receive parts by sea rather than by overloaded transport aircraft. The operational tempo increases immediately. The early missions follow doctrine established in Europe: high-altitude precision bombing from 30,000 feet in daylight. The results are disappointing. Japan's weather produces cloud cover over targets 80% of mission days. Bombing through clouds using radar achieves accuracy measured in miles rather than feet. The high-altitude jet stream, unknown to American meteorologists, produces winds exceeding 200 miles per hour, pushing bombs miles off target. Curtis LeMay analyzes the numbers. The B-29 is burning fuel and risking crews for minimal damage to Japanese industry. High altitude provides safety from fighters but prevents accurate bombing. The pressurization system, the engine development, the entire design philosophy is predicated on operating at 30,000 feet. LeMay decides to abandon it. March 9, 1945. LeMay orders the B-29 force to attack Tokyo at 5,000 feet at night with incendiary bombs instead of high explosives. The decision violates every principle of strategic bombing doctrine. It exposes the aircraft to anti-aircraft fire. It eliminates the defensive advantage of altitude. It risks the entire bomber force on a tactical gamble. 334 B-29s strike Tokyo in the largest single bombing raid in history. They drop 1,665 tons of incendiaries. The firestorm kills 100,000 people and destroys 16 square miles of the city. The B-29 suddenly becomes the most destructive weapon in the American arsenal. Not because of its sophisticated systems, but because LeMay recognized that the aircraft's true capability was carrying massive payloads over strategic distances regardless of altitude. Tinian, August 1945. A B-29 named Enola Gay sits on the hardstand, modified to carry a single weapon weighing 9,700 pounds. The bomb bay has been reconfigured. The crew is handpicked. The mission profile is unlike any flown before. One aircraft, one target, one bomb. The Manhattan Project required a delivery system. It required an aircraft capable of carrying a weapon the size of a truck over strategic distances, delivering it with precision, then escaping the blast radius before detonation. Only the B-29 possessed the payload capacity, the range, and the speed necessary. The atomic bomb program existed because the B-29 program had succeeded. Hiroshima, August 6th. The atomic bomb detonates at 8:15 a.m. 3 days later, Nagasaki. The B-29 delivers the weapons that end the Second World War. The aircraft dismissed as too complex, too expensive, too ambitious becomes the instrument that makes invasion of Japan unnecessary. The Marines who would have died on Japanese beaches live because the B-29 flew. The program cost $3 billion in 1940s dollars, more than the Manhattan Project, more than any weapon system in history. The aircraft suffered catastrophic failures throughout development. Engines burned, systems failed. Production nearly collapsed. Critics predicted disaster, but the B-29 delivered strategic bombing capability that determined the outcome of the Pacific War. The technological legacy extends beyond the immediate conflict. Pressurized cabins become standard in commercial aviation. Remote fire control systems evolve into modern aerial gunnery. High-altitude performance drives jet engine development. The B-29 program pushes American aviation technology forward by a decade, creating capabilities that define the post-war aerospace industry. But the true measure is simpler. The B-29 did what it was designed to do. It reached targets 6,000 miles from friendly bases. It carried payloads exceeding anything previously possible. It operated in conditions that would have destroyed lesser aircraft. And when the moment arrived, when history demanded an aircraft capable of delivering the atomic bomb, the B-29 was ready. This is how the bomber nobody believed in won the war. Not through perfection, but through persistence, solving each impossible problem until the impossible became operational reality. If you're listening right now, help me prove something wrong. My friend, who is a chimerical pilot, said I wouldn't even reach 1,000 subscribers. But I believe stories about airlines and the realities of modern travel like this deserve to be told. Help me show her that these videos matter. Please subscribe to the channel and let's keep these stories from being buried.